Let's Talk Chemistry with Pastor Dan. We're looking at radioactive decay, a process of radioactive material breaking down, so we go from material going back and forth all the way down till we get to the almost infinitesimally small to almost like negligible, but in reality we never get rid of all the material. So when we deal with radioactive decay, the equation we use looks like this. A to the t, in other words, how much we have, the amount that we have right now at the given time, is equal to a to the o, how much I had at time 0 or originally, times e, that's the natural log base, 2.19, blah, 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 raised to the minus kt. Now, k is a constant and t is time. So, at is the amount of that remains, ao, the original amount, the original, e, natural log base, 2.19 is the way that function works, and t is time. Now, k is a reaction rate constant. The way that we find that is we take 0.693 over t1/2. Now, where do we get 0.693? Half-life is the amount of time for half of it to break down. So if I have half of it, that's 0.5. So you take your calculator, put the natural log, ln, of 0.5, we get negative 0.693, but because that negative is number up there, we're just going to keep it positive. So that value, or t1/2, is the half-life, how much time it takes for the reactive material to break down. That's what that means. All right, now, we also have another way we can do that. We can also use the equation ln of at over ao is equal to minus kt. If I'm trying to get at k or t, the natural log is the inverse function of the natural log. So the ln function helps us get at what's inside of there. And we use that. If we're solving for at or ao, we're going to use this first function, okay? If anything, we're solving for k or t, we're going to use that second function. So we use each of them based on what we're solving for. Okay, let's take a look at a couple of these. All right, for this one, determine the amount of reactive isotope that remains after 2.500 years if the half-life of reactive isotope is 3.165 days and the amount of originally reactive substance is 123.5 grams. So we put our anode values, our AT, AO, KT, for graphic organizer. We want to identify our value. Well, AT, the amount we have that remains, now we have right now, that's unknown. That's what we're looking for. AO, how much we have originally. If you look at the number, original reactive substance is 123.5. K, again, we said was 0.693 over t1/2. And we look at the problem. The half-life is 3.165 grams. So we divide that through. We get 0.2190 per day. And we go off of sig figs here. This is 4 sig figs. This is infinite because it's a constant given to us. So we're going to go with 4 sig figs. And then time is 2.500 years, but we want it in the same unit as my k value, so they'll cross out. So therefore, how many days in a year? 365.25. Remember, leap year every 4 years. So we got to put a quarter of a day in for every year. And we multiply through 4 sig figs there, or you can get 913.1 days. All right, so which equation we're using? We're solving for AT, so we went back, we're saying we're going to use that first one. We're solving for AT. All right, so we don't have to rearrange it. It's already set up for it as is, where is. So let's put our values in. AT, AO is 123.5. E raised to the negative 0.1290 per day and 913.1 days. Now, when we use our units here, so we can see they cross out, days cross out, we're left with grams. Now, there are two types of calculators you can have. You can have the one that scrolls across the top. If that's the case, then it's easier to use this. They also have ones like this over here. And what you end up doing is you do the number inside of here first, and then take the e function of it and then multiply. So you basically work wherever's inside of here first, take the function of that, and multiply through it. So taking your calculator, let's do it this way first, type it in 123.5 times E, and then it's going to be negative 0.2190 times 913.1, close parentheses, equal. If we're doing this one, I'm going to start with the E, type in 0.2190 times 913.1 equal, make it negative. Second function E equal times 213.5 equal. When you do that, you should get 1.73 times 10 to the negative 85th grams. Really, really small number. All right. Hope that wasn't too bad. Let's try the next one. Calculate the half-life of radioactive isotope. It takes 2.245 days to go from 19.67 grams to 13.78 grams. All right, so our graphic organizer again. AT, AO, K, and T. Put our values in. Look through there so you can find them. AT is 13.78. That's at the end. How much we have originally? 19.67 grams. K is 0.693 over T1/2, but I don't know T1/2, so it's my unknown value. And K is 2.45 days. We don't have to change anything else because days is what we have. All right, so which equation we're working for K? So we're going to use that second equation. Ln of AT over AO is equal to minus KT. Now, we're not set up to solve for unknown, so we're going to have to rearrange here. K, we're going to move the T over and the negative over. So when we divide it through algebra 1 here, we're going to get ln of AT over AO divided by minus T is my K value. Put our values in. Ln of 13.78 divided by 19.67. And our T value is negative 2.245. So what you can do here is if your calculator is like this one again, you type ln and then 13.78 divided by 19.67, close parentheses, equal, divide by negative 2.245 equal. This one you're going to do inside the calculator first. 13.78 divided by 19.67 equal natural log equal, divide by negative 2.245 equal. When you do that, grams cross out, we end up with 0.1585 days per day, right? But that's K, and I don't want K, I want half-life. So remember we said that K is 0.693 over T1/2. So those values are numerator and denominator. We just swap partners. T1/2 comes up, K comes down, and we're going to say that T1/2 is equal to 0.693 over K. Put our value in then. 0.693 divided by 0.1585, 4 sig figs. When we do that, we get 4.372 days. All right. Let's do one last one. And this, again, is why I have to do radioactive decay, so let's make sure we go through this one. How old the sample? There originally was 12.88 grams of carbon-14, and there's presently 4.399 grams left. Now, this is carbon dating, and you know how I feel about it. It's good to 10,000 years, so all my values will be under 10,000 years because that's as accurate as we can really be. All right, our values, AT, AO, K, and T. Put them in there. Pause the video, see if you can find them for yourself. All right, we should get 4.399 grams, 12.88 grams, 0.693 divided by 5715. Now, that wasn't given in the problem, so we're going to consider that infinitely significant. So we divide that through, and I'm going to put in scientific notation. I get 1.212598.425 times 10 to the minus fourth. That's as far as it went on my calculator. I'm going to consider all those important. Not worry about it. And T is unknown. All right, so we're solving for T. So we're going to use that second equation. We're going to use this one. Now we're solving for T. So rearrange it. K is going to go in the bottom. Negative K is going to go bottom. T is equal to ln of AT over AO divided by minus K. Put our values in. So we're going to take 4.39 natural log of 4.399 divided by 12.88 grams, and then we're going to divide that. Okay, let's go a little slower this time to make sure we got this down. Take your calculator, hit ln. You should see a parenthesis on there. 4.399 divided by 12.88, close parenthesis, equal. Divide by negative 1.212598425. EXP 10 to the x, however the calculator reads it, negative 4 equal. On this calculator, I'm going to start inside the parentheses. Type in 4.399 divide by 12.88 equal. You should get a decimal. Natural log, you should get a negative number. Divide by 1.212598425. EXP 10 to the x minus 4 equal. When you do that, you should get well, grams cross out, of course, and my answer is going to be in years. It's going to be 8,859 years because I have 4 sig figs, and that K value is infinite. That's my answer. All right, let's do one last one then. And this I'm going to have you do it on your own. Determine the mass of iodine that is there originally, if it presently is 0.98748 grams remaining in the body after 2.500 weeks, when the half-life of carbon is 5.842 days. We're going to solve for A to the O. So we're going to use, remember which equation we're going to use? We're going to use A to the O first. Plug our values in, rearrange them, and then remember to do the function. And depends on which calculator you have, how you do it. Pause the video, give it a shot. All right, here we go. When we do that, we're going to solve for AO is AT over e to the minus KT. K is 0.1186 per day. We're going to convert 2.500 weeks into days, so that's 14.50 days. Multiply through, we get 7.767 days. All right, that's it. Hopefully it wasn't too bad. We'll practice these next, and then we'll do a lab on these, and we'll go from there. All right, sounds good. Take care. Be good.